So, section 2.2, page 104, we're looking at. So, inverse functions, because inverse functions, the way you've written them, when you go through math, you always have this 5, and you write the inverse rather than 1/5, you write it this way, and it always equals 1. Now, the nice thing about invertible matrices is that they're commutative. You can't, other matrices, you got to do it one side or the other, and you can't, they're not commutable. If a matrix is invertible, it's got to be a square matrix, and it's commutative. So no matter which side you do it from. So the notation for A, if it's invertible, is going to be A inverse. And then the nice thing about this is that you can do A inverse A equals A inverse, and both of them equals the identity matrix. So if it's invertible, that's going to be the case method. It's going to be commutative, and that makes it nice, and that makes it real able to translate back to what we have learned in math when we're doing inverses. Now, you notice on the page 105, it says a matrix that is not invertible is sometimes called singular. And if it is invertible, then it's called non-singular. They have at the bottom of the page a formula for finding the inverses. Now, this is an inverse of a special matrix. It's a square 2 by 2. So if you have a square 3 by 3, if it's invertible, non-singular, you can't find it using this method. There's other methods, but this method. And the method is that, I guess, just comment a little bit about this. If your matrix, 2 by 2 matrix, is A, B, C, and D, then your invert for that is going to be this 1 over A, B, okay, B, minus B, C. And then what you're going to do is you're going to interchange the D and the A, and you put a minus sign in front of the B and the C. And then you do that multiplication with this. Now, a couple comments about this. Right underneath there it says the determinant of A is this AD minus BC. So when you see that called the determinant of that, and it's got to be a 2 by 2 square, because you can see that you can't get, if you had a 3 by 3, you couldn't get a determinant in this same general way. And then if AD equals BC, then it's not invertible. Because then this determinant will turn out to be what? If this is the case, then the determinant of A equals 0. So, and then you'd be 1 divided by 0, and that'd be an undefined number when you came that determinant, and so on. All right, so then the next page there, it says the theorem 5, A is an invertible n by n matrix. So it's got to be square. Then for each B in Rn, the equation AX equal B has a unique solution, A equals A inverse B. So this AX equals B. X is equal to A inverse B. If A is square and if it's invertible. And now this is not for just a 2 by 2, but this is for any matrix. 3 by 3 or 4 by 4 or whatever it is. It's going to be that way. Now, just notice on the next page on 107, where the second paragraph, it says the formula in theorem 5 is seldom used to solve the equation AX equals B numerically because row reduction of AB is nearly always faster and more accurate. So if you do an augmented matrix and do your row reduction, that's a faster, easier way than to try to solve it this way. And it's more accurate, especially when you get into some decimals and things. So that's just kind of a warning about that. Theorem 6 says A is invertible matrix, A inverse is invertible, and A inverse inverse is equal to A. AB is n by n invertible matrix, then so is AB. And the inverse of AB is the product of the inverses of AB in reverse order. So they gotta be reversed. Okay. A is an invertible matrix, and so is A transpose, and inverse of A transpose is the transpose of A inverse. If there was anything. On 308 or 108, they're talking about an elementary matrix. And that's an elementary matrix is whenever you perform single elementary row operations on an identity. So you take an identity and just do operations on it, then you do an elementary matrix. And at the bottom of the page it says an elementary row operation is performed on an m by n. Now this is not necessarily a square matrix. The resulting matrix can be written as EA, where m, the square matrix, m by m, E is created by performing the same row operation on IM. Okay. And then E is invertible. So on the theorem 7 says A is invertible if and only if it's row equivalent to IN. So it's saying that A can be reduced to IN, row equivalency, if you do a reduction on it. And then it says, in this case, any sequence of elementary row operations that reduces A to IN also performs IN into A inverse. Okay. And so that really gives you a way to find the inverse. Some places. You can find the inverse of, because if you, that theorem says that if you do an A and an I N, and you convert, you do row operations so that the A turns to I N, then this will be A inverse. So if you just augment the A matrix with IN, and then on that whole matrix you convert the A into IN, then that operation will convert the IN into A inverse. And that's what that theorem is really telling you. Where it's, yeah. That when you do those, it says, if A is invertible, if and only if A is row equivalent to IN, in this case, any sequence of elementary row operations that reduces A to IN also translates IN into A inverse. So that's telling you that if you convert this into here, then this will go into the A inverse. So you can find the A inverse of any matrix by just doing that kind of a thing to it. Does that make sense? And that's what that theorem tells you can do it. If you want to have something challenging, just try proving that. Okay. Okay. Oh, here's the algorithm. The next page. That's where it's saying that the row reduce the augmented matrix AI. If A is a row equivalent of I, then AI is row equivalent to IA inverse. And this is what it's saying. So it's a way to get the inverse of an A matrix that's not 2 by 2. Because that first theorem in this section, you can only get the inverse of a 2 by 2 matrix. This method, you could get the inverse of a 3 by 3 or 4 by 4 or whatever, but it'd have to be a square matrix. And then it's going through an example, and then at the bottom of that example it says it's a good idea to check the final answer to make sure, and the checking of it would be that you would do A times A inverse. And when you do that, make sure that you come up with I. Okay. Now, there's a note there on page 111. It says, in practical work, A inverse is seldom computed unless the entries of A inverse are needed. Computing both A inverse and A inverse B takes about 3 times as many arithmetic operations as to solve AX equal B, augment the matrix and do the row reductions. So, it'd only be if I would say you've got to do the A inverse of A, which is a 3 by 3 matrix, that you go through that process. Otherwise, if you're trying to solve something to use the A inverse, you wouldn't do it. Okay. So let's look at problems. The inverse of a matrix. And so problem 2 is telling you to find the inverse of this matrix. 3, 7, 2, 4. So that is that theorem back on page 105. Okay. Now, the first thing you got to do is you got to get this determinant of A, which is that AD minus BC. And remember that the way you number these things is A, B, C, and E. So then the values are going to be 3 times 4 minus 2 times 7. Minus 2. And then what you do is the formula says that you got to do 1 over the determinant of A, and then you have to interchange that. You interchange the D and the A, then you do a minus the B and minus the C. So that's 1 over minus 2. And then you would have 4 minus 2 minus 7 and 3. And then this is going to be minus 2, 1, minus, no, plus 7. And negative 3. 7 halves. So that should be the inverse. And you're just using that theorem back. Okay, for the problem, I'm going to do another one of those. And I'm going to do 3, although it's one I normally would have you do. But the reason I'm doing 3 is because I'm going to use it in 6. So 3. 8, 5. Okay, and that determinant is AD, so 8, it's AD minus BC, so it's 8 times minus 5 and minus 5 times a minus 7. Minus 40 plus 20, so we get a minus 20. And then we want to interchange this matrix. I want to put 1 over minus 20. And then this is going to be a minus 5 and 8. Did I do it wrong? Oh yeah, I don't know how I did 20. Thanks. Jeez. Okay. So it's a plus 35, right? And this is going to be a minus 5. Okay, thanks. Sometimes those things happen. And I guess in this case it happened. Minus 5 and a plus 7, right? So then it's going to be 1, 1, and then a negative 7/5. And a negative 8/5. Okay, got that right, didn't I? All right. And 8. And 8 is going to, 6. 6. And 6 is saying use the inverse found in exercise 3 to solve the system. So I'm just trying to save myself a little bit of time here. So the inverse, we've already found it. And then let's see. Okay. Since AX equals B, then what this is saying, this is going to be the matrix 8, 5, minus 7, and 5, minus 5. Because what they're telling you is that 8x1 plus 5x2 equals minus 9, and then a minus 7x1 plus negative 5x2 equals 11. So you can write this in matrix form this way. Right? And the 8, 5, that comes from those two right here. 8 and 5 go right over here. And minus 7 and minus 5 goes here. But that is this matrix here that we found the inverse. And this is A inverse. So we're going to use the method of AX equals B. We're going to do A inverse AX equals A inverse B. This right here is I X. So X is equal to A inverse B, and that's so that's how come we're going to do this way, and then we're going to do that inverse matrix. So X is going to equal, and the inverse matrix is 1, 1, minus 7 fifths, and the minus 8 fifths. Minus 8 fifths. And then the B, minus 9 and 11. Then we multiply, right? So we have a minus 9 plus 11. Then, I'm doing, how come it was on that? I'm doing that times there, and that's how I'm getting that solution, right? And then 2 fifths, is that 7 fifths? 7 fifths, isn't it? 7 minus, so that's a plus 7 fifths times 9. So 7 times 9 is 63. 5 plus 8 times 11. How about minus? Minus 88 over 5, right? minus 8/5 times 11. So this is going to be the matrix 2 and common denominator, so then we go 5, 25, negative. Then we reduce that down. So it's 2 minus 5. Okay, if I didn't make any mistakes, that should be the answer. Does that look good? All right. Okay. Number 8 says use matrix algebra to show that if A is invertible and D satisfies AD equals I, then D equals A inverse. Okay. So A being invertible leads to A inverse exists, right? And if that's the case, then A inverse A equals I. So then what we do is AD equals I, and that's given, right? So then we do A inverse of AD equals A inverse I. And then we can rewrite this as A inverse A equals A inverse. Because I times any matrix is that matrix. This right here, by definition, is I times D, and I times D is A. Therefore, D is invertible. So that's using matrix algebra to show that D equals A inverse, and D is therefore invertible. All right, 10. It says a product of invertible n by n matrices is invertible. And the inverse of the product is the product of their inverses in the same order. Well, that has to be false, because if you look at theorem 6, so this is 10. And you look at part B, it says that A, B inverse equals B inverse A inverse. In that statement, it's stating it wrong. It says the product of invertible n by n matrix is invertible, and the inverse of the product is the product of their inverses. They're saying what they're saying, which is a false statement. That's what they're saying. But the theorem says, no, it's AB inverse is equal to B inverse A inverse. So that it's a false statement. B is false. And then B says if A is invertible, then the inverse, A inverse, is A itself. And so that one is true. Because A inverse, the inverse is A. And that's theorem 6, part A. And C says if A is equal to AB, CD, and AB minus CD is not equal to 0, then A is invertible. And that's true. It says it's not equal to 0. Yep. Oh, I was looking at 9, not at 10. 10C. Okay, that one is false. I slipped up and looked at the wrong one. This is false. That's because the determinant in that theorem 4 which says that AD minus BC and AD minus BC cannot equal 0. But if this were true, if AD equals BC, then AD minus BC would equal 0. And then theorem 4 says not invertible. No, if they're equal, then it, well, let's see, how does it read? No, oh, so then it'd have to be, because the way it's written, it'd have to be true. It's not invertible. So that would be true, thanks. This would be true because it's not invertible. And the statement there in 10 says it's not invertible. I thought it said it was invertible. So, all right. If A can be row reduced to the identity matrix, then A must be invertible. And that would be true, because theorem 7 says if A is invertible, if and only if A is a row equivalent to I, and if and only if means the other way around. If A is row equivalent to IN, then A is invertible. So that's D would have to be a true statement. Because true T. Because anytime it says if and only if, it means if the first, then the second, if the second, then the first. And if the second, A is row equivalent to IN, then A is invertible. And that's what this is saying. If A is row reduced to the identity matrix, then A must be invertible. So theorem 7 is stating that's true. E, if A is invertible, then the elementary row operations that reduce A to the identity IN also reduce. No, that statement is false because E is false. Because it should say the row operations that make A to I will cause I to go to A inverse, not A inverse to I. Because that's what that theorem says. It says theorem 7. It says an invariant matrix A is invertible if and only if A is row equivalent to IN, and in this case, any sequence of elementary row operations that reduces A to I is also transforms IN to A inverse. And you see that statement there in 10 says that it reduces A inverse to I. It should say I to A inverse. It says I to A inverse, not A inverse I. So that's what makes that statement incorrect. So this is the false statement. He is. Okay, 14. So suppose B minus C D equals 0. Where B and C are M by N matrices and D is invertible. And then we want to show B equals C. Okay. So if D is invertible, then D inverse exists, right? And we can do, and that means this, that means D inverse D equals D inverse equals I. So if we take B minus C D and we multiply this on that side, then what we have is we have B minus C I equals, and this is 0. Because 0 times any matrix is 0. And I times any matrix is the matrix. So B minus C equals 0. And we can add matrices to both sides. So B equals C. Okay. So that would be how you prove it. And I should do by theorem, but I guess I didn't. 16. Suppose A and B are N by N, B is invertible, AD is invertible. Show that A is invertible. And they're saying the way to do it is have C equal AB and solve this equation for A. So we're going to use their suggestion. So C equals AB. And E invertible. So that means, once again, that means that we can do B inverse B. We can do B inverse. And always get I. And it's important that we can do it on both sides. Because if you could only do it on one side, then you may get, and if matrices aren't commutable. So you see, if I could only do it, it's important that this can, B inverse can be multiplied by both sides, because it could only be multiplied by one side, and it had to be multiplied by as B inverse B to get I. You couldn't commute this. You couldn't commute this because matrices aren't commutable. Understand what I'm saying? So we can left side, right side multiply this thing. So that means that this, we're going to take the C B inverse and do A B inverse. And C B inverse equals A I, and C B inverse equals A. But C equals A B, and A B is invertible. Therefore, C is invertible, and C B inverse, an invertible matrix times an invertible matrix is invertible. Therefore, A is invertible. And it's pretty important that you stipulate that C is invertible, because you're substituting C for AB, and AB is invertible. Okay. And 20 is saying, suppose A, B, and X are n by n matrices with A and X and A minus AX all invertible. So A, X, and A minus AX are invertible. And then they're saying A minus AX invert equals X invert A. And then they say, explain why B is invertible. So what I'm going to do is I'm going to right multiply x. So that is telling me that and now B is a product, A is invertible, and A minus AX is invertible, so B is a product of invertible matrix. And so theorem 6, B says if A and B are n by n invertible matrix, then so is AB, and the inverse AB is true. Let's see, is it argue AB? Is that the theorem I want? That's what. There's a theorem that says it. That wasn't the one I wanted. This would be I thought that one was going to do it. If A and B are n by n. Yeah, I think I can use that. These two are invertible matrices. That makes this one over here invertible by theorem 7b. Yeah. Okay, then the B part of that 20. This is the A part. Okay. So it says solve that equation for x. If you need to invert a matrix, explain why the matrix is invertible. So if we're given AX invert, okay, focus on what we're doing. We're trying to solve for x. So if we invert both sides of that matrix, both sides of that equation, and that says that the invert of an invert on the left-hand side. It says that this is a minus ax equals, and then this is going to be x invert, invert, b invert. And that is this right here is true by theorem 6a. This is true by theorem 6b. How's that?
I was about to say, if you're inverting the right side of the equation, it should be the inverse times x.
Oh,
Because whenever you invert the multiplication,
yeah, you're right. This is supposed to be the way around. It's supposed to be b inverse x inverse inverse. So an a minus ax, b inverse, and this is x. Now if we add the ax to both sides, and then we factor. Plus a. We factor that x out. And they said, what did they say? They said that I guess I'm going to give you the quiz because it's time. I'll look at that and try to get it better.